welcome everybody. We can get started. So this is the ASTRA-sim tutorial, enabling hardware-software co-design of distributed deep learning training platforms. This tutorial is also being recorded. So just to kind of, formally welcome you all. So I'm Tushar Krishna. I'm an associate professor at Georgia Tech. And my co-organizers here are Taekyung Hyo and William Won, who are here in person, and Saeed Rashidi and Srinivas Sridharan, who will actually be presenting virtually. So William is currently a PhD student at Georgia Tech, Taekyung is a postdoctoral fellow. Saeed recently graduated from Georgia Tech, and Srinivas is a research scientist at Meta. We, of course, this project itself has had a large set of collaborators and contributors. So Darshan Srinivasan from Intel, folks at UT Austin who've developed some key enhancements, and there's actually a new set of people who've been contributing to it actively as well. So this is the agenda that we'll be following. So my plan is to give everybody a brief overview of distributed deep learning training. So this is not meant to be like a full-fledged deep dive. There's a lot of resources on that you can leverage, but at least it, wanted to introduce the terminology that we'll be using, which will also help understanding the simulation infrastructure itself. Then Srinivas will actually give an industry perspective, wearing his Meta hat on some of the training systems challenges. Then we'll actually introduce the ASTRA-sim tool. So Saeed and Taekyung will walk over some aspects of the tool. Then we'll time the coffee break with the break that we have at the conference. Then we'll continue with ASTRA-sim's description, going into more details on the other layers of the tool. And then William will will kind of present some of that and also do a quick demo of some of the features, some of them that are more recent that we haven't covered in previous tutorials. And finally, just closing remarks and questions. So this is the tutorial website that has, the agenda, slides, installation instructions, and so on. And as I mentioned, the tutorial is also actually being recorded. So these are the steps. Like if you actually go to the tutorial website, you can actually, these are the steps to kind of get the tool installed. And as I mentioned, there's also, other resources there, including the papers that describe the tool. All right, so with that, let me get started and give you all a quick primer on just distributed deep learning training. So, of course, the engine driving the AI revolution has actually been a lot of data, right, that is fed into models, right? So we've seen AI having huge impact across vision, speech, language, recommendation systems. In fact, if you followed the news more recently, like large language models due to generative AI is kind of everywhere, right? And so really the idea is you take a lot of these data samples, feed them through your model, and training really just involves, updating the weights to model the underlying function that represents the data set. And if you've kind of trained it well, it generalizes beyond just the specific training data samples that you use for training. So in the context of, ML, if you kind of really think very broadly, ML algorithms can be categorized on like several characteristics, like the task that you're trying to solve, how you are leveraging feedback from data, and the specific method that you're using for hyperparameter optimization. So within this large breadth of like ML, our focus will be on supervised learning with stochastic gradient descent, because that is really most popularly used for deep neural networks. So it is, just want to acknowledge, is a subset of the broader field of machine learning. So within now DL training, it typically operates in the following phases. So there's the forward pass or the inference phase, and then there is the backward pass, which consists of weight gradient computation and input gradient computation. But together, the backward pass is called backpropagation. And we'll use a term called training loop many times in this tutorial. The training loop is really going to determine the order in which we issue the basic operations and possibly their related, communication tasks. So the training challenge, of course, is the fact that, training time is becoming larger and larger, right? DNNs are becoming larger and larger. Again, I briefly mentioned, billions to now trillion parameter models. Training samples are becoming larger, especially if you're training things like recommendation models. You're kind of collecting data over and over again. And, Moore's law has ended. So you can't just rely on, computers to become faster and faster to address this gap, right? So this is this chart from OpenAI that's often used to demonstrate that, starting from AlexNet that really kicked off the deep learning revolution, to AlphaGo 0, which is where, basically the AI beat a human player in the game of Go. There was a 300,000x increase in compute, right, to train that model. So that's something that kind of goes beyond the typical exponential curve we expect just from Moore's law, right? So really need to do something different, right? The other challenge is that as you have models becoming larger and larger, the communication demands of these models also becomes large. So you have large models, you need multiple accelerators. So we're going to use the term NPUs or neural processing units to mean accelerators. Like these could be GPUs, these could be TPUs, these could be FPGAs, these could even be, CPUs. So like multiple of these are required to just fit the model, right? If you have like billions or trillions of parameters, you cannot fit in the 16 gigs of memory a GPU provides you. So you need like tens of GPUs simply to fit the model. And then you need even more if you want to kind of get parallelism and scale performance, right? So just as an example, to just fit, GPT-3, you need about 16 GPUs. And if you use the 0 stage 2 optimization method for training a 1 trillion parameter transformer, you'll need 128 NPUs. So this is where there's been a recent surge in what we're going to call DL training platforms, right? So several companies are essentially building customized platforms that are meant for AI training, right? So you'll hear terms like AI supercomputers. That's the term that a lot of these companies are using. So, the Google TPU v3 is an example, NVIDIA's DGX, Meta has Zion. Meta also has another platform they had released recently. So essentially, the idea is let's build customized chips for training. Again, these could be GPUs, these could be TPUs, these could be FPGAs, and let's scale the training across more and more compute nodes. And there's many more, right? So, there's different kinds of solutions people have looked at. There is kind of the traditional way of scaling through off-chip interconnects. There's a recent interest also in trying to scale using advanced packaging technologies. So if you follow what Tesla's Dojo did or Cerebras wafer scale engine, there is, other approaches like Intel's Habana, IBM Blue Connect, and so on. So this is basically what a DL training platform looks like from, let's say, a 100-foot view. So you have a bunch of these endpoint nodes where you have, I don't know if my mouse is visible here. Maybe not. Fine. So you basically have a bunch of endpoint training nodes. So I'm trying to see if my mouse can. Actually, let me go into this one, right? This one. Yes, perfect. Thanks. So you have a bunch of endpoint training nodes here. I have my training accelerator or NPU, the CPUs and NICs. So you'll notice like two kinds of networks here. There is a scale-up fabric connecting all the NPUs together, and there is a traditional scale-out fabric connecting via NICs, right? So the NPU here is something that is a key component of these platforms, and so are these interconnect fabrics, right? Both the scale-up and scale-out. So some of the key systems challenges with distributed training are really about communication, right? This is inevitable, of course, in any distributed algorithm. And the communication really depends on a few things, right? It depends on the synchronization scheme, the parallelism approach. But the question is communication really a challenge when it comes to distributed training? Well, the answer is it really depends. It depends on whether we can hide it behind the compute, right? So if you had a very nice, well-balanced system with some, compute capability for all of your accelerators, as long as those accelerators are active every cycle, that's perfect utilization, and communication is hidden, then that's the best you can do. But the challenge becomes when your accelerators are idle because they are waiting for communication tasks, right? And that's really the challenge. And so how do we determine this, right? And that's really where ASTRA-sim comes in, right? So our goal is to try and understand the deep learning training design space. And this figure, courtesy Meta, kind of tries to break down the entire hardware software co-design stack across various tiers. So we've kind of divided it into what we call as a workload layer, a system layer, and a network layer. And I'm kind of going to go through each of these one by one, just to kind of give you a quick preview of the kinds of challenges in each tier. And ultimately, of course, the overall challenge we're solving is a co-design challenge that is cross-coupled across all of these tiers, right? So at the very top is the model that you're trying to train, right? So this could be, so you kind of have the model that you're trying to train. Then you have to take this model and, parallelize it across all of your available compute, like memory resources. Then you have the actual communication policy and pattern that you implement. Then you do framework level scheduling. All of this is now done, on your actual resources. So this is your compute and memory resources and some of your communication resources, going down to the network stack, which includes the messaging transport layer, your endpoint node design, connectivity, your fabric architecture, topology, and finally low-level network implementation, which will include things around coordination, buffering, flow control, congestion management, and so on. And of course, this is the classic tussle, right? In anything like this, where abstractions are great. Abstractions actually allow you to work independently in each of these tiers without having to worry about the other tier. But if you really want to do co-design and co-optimize, then you really need to break these layers, right? So that's why this is kind of the tussle that like almost all hardware software co-design challenges deal with. And here it becomes even more complex given like the levels of the stack, which includes as in workload level optimization, system level optimizations, and more hardware level optimizations. So let's start with the very top of the stack. So that's where it's the DNN models. So these are some of the very common models in use today. So things like ResNets in vision, transformers are becoming almost ubiquitous when it comes to language and speech, and things like recommendation models, right? So from the perspective of what we care about, we care about like the specific kinds of operators that exist within each of these models. So these could be convolution operators, attention operators, fully connected operators, and so on. And the sizes, right? The parameter sizes or weights, which, as I mentioned, could be millions, billions, or trillions today. So then we come to the parallelization strategy. This is really the way the compute tasks are distributed across many compute nodes, right? And there can be many ways to split the tasks. You can kind of split it across the mini batch, which is called data parallel. You could split the model itself, model weights, across different memories. That's called model parallel. Or you could kind of split the layers and like map them across all of your NPUs. That's called pipeline parallel. And this also defines the communication pattern across different nodes. So for example, if you're doing data parallel training, the basic idea is that we're going to distribute the data across multiple nodes and replicate the model, right? So you essentially take the data samples, split them across the memories of these NPUs, and the model or the weights actually get replicated. So this leads to, no communication during the forward pass, right? Because each NPU has a copy of the model. It just has a subset of the weight, the inputs. It sends them through. So there's no communication in the forward pass. But in the backward pass, you actually have to communicate weight gradients during the backprop, right? And so you essentially have a blocking weight at the end of back propagation for the collective before you do the next forward pass. When you do model parallel, the idea is now you actually split the model weights across the different NPU memories and the data samples get replicated. So here, because every NPU only has a part of the model, even during the forward pass, you actually need to communicate as you're kind of going through different layers. And this is a blocking communication, right? Because you need to kind of wait for like this NPU to complete its computation, exchange compute the output, agree on the common output, then move on to the next layer and so on, right? So you need to have these activations flowing through. And then in the backward pass, again, you have communication of the input gradients and the weight gradients during backward pass. So just at a very high level, what you'll notice is model parallel ends up having a lot more blocking communication, which is why it's usually much harder to optimize for. And data parallel is more common and prevalent. But as I mentioned, right, as you have larger models, you cannot just rely on data parallel because you have to fundamentally distribute the weight. So this becomes a challenge. So this is where there's also hybrid parallelism schemes that are often used, where if you have a very large model, let's try to split the model across NPUs to kind of till some point once we can fit the model, and then across these groups or clusters, let's do data parallel. This is used quite often. This now means that in terms of communication, you kind of have a hybrid communication, right? Where you have partial activation communication during the forward pass as well, and weight and input gradient communication during the back pass. Another common parallelism scheme is pipeline parallel, where you're actually trying to, distribute all the layers across all the NPUs. And so now here, during the forward pass itself, as each layer does its computation, it forwards the activations to the next layer. And during the backward pass, you have, you have your, again, input gradients being communicated for computing the final errors and updating the models. So pipeline parallel has its own challenges. I mean, like as with any classic parallelization scheme, you kind of have issues of, bubbles in the pipeline. So you really have to think about breaking the mini batch into smaller micro batches and schedule them in a way that you minimize pipeline bubbles. And of course, so these are just three broad classes of schemes, right? But models are becoming larger, as I mentioned, compute models are becoming larger and more sophisticated, right? So there's actually a need for more and more sophisticated parallelism schemes. So this is a very active area of research today. So things like Microsoft Zero is a very interesting scheme where it identifies that you cannot fit large models. With model parallelism, the challenge is there's a large communication overhead, almost, and there's also a lot of memory overhead because of intermediate optimizer states. So Zero is a very interesting scheme where you actually partition the optimizer state and gradient state. And again, without going into details, the idea is like, depending on the specific Zero optimization scheme you pick, you go from a baseline scheme where you needed, let's say, 120 gigabytes to this one where, if you use all the optimizations, OS, GNP, you need only about 2 gigabytes. So the fundamental idea is you're trading off like memory and communication and kind of only communicating the optimizer state when needed. So it's a very interesting scheme, but essentially it just means that the communication behavior is even more sophisticated than the very simple examples I gave with data model parallel. DLRM also has a very interesting parallelization strategy. So in DLRM, the embedding tables are extremely large, again, cannot fit in the memory of a single accelerator. So the embeddings actually end up using model parallel, while the MLP layers use classic data parallel. So now from a communication perspective, again, you have your output activations like once you kind of go through the embedding layer, you actually have to do an all-to-all and wait for this all-to-all to finish. And then like once the bottom half of the MLP layers are done, then you run the top half. And during the backward pass, you have input and weight gradients being communicated. You do an all reduce. This is just classic all reduce because you're doing data parallel. And then again, you have to issue an all-to-all to kind of synchronize with the embedding layers, right? And then wait for this to finish. So again, the idea was to just show you how some of the communication becomes more sophisticated. Of course, there's, again, as I mentioned, more sophisticated examples as well. So Pipedream from Microsoft, Megatron LM from NVIDIA, and you might have again followed the news with a lot of companies trying to play around with different kinds of schemes. So I think very recently, NVIDIA and Microsoft again announced how they're working together on building platforms like this. So that's a parallelization strategy, right? A very active area of research. So once you've decided a parallelization strategy, the story doesn't end there. Now you have to think about what is the communication policy and pattern and the framework level scheduling challenges. So once you have your model, there's kind of this grid of ways of performing synchronization. So you could either have an asynchronous training scheme or a synchronous training scheme. So asynchronous training, this really just decides when nodes should exchange data and affects convergence time, right? So asynchronous basically means that, as soon as different nodes are computing their gradients, like they can move on, while synchronous really needs to wait for everybody to be complete before, you communicate. And like from an accuracy perspective, and convergence perspective, the usual preference is on synchronous training, and that's what we'll consider. There's also communication handling. So, okay, once I mentioned a few times about, okay, NPUs need to communicate. Well, how do they communicate? Either you have some central parameter server where like all the, model weights and activations are stored and all the communication is via this central server. So in step one, each node sends its gradients to the parameter server to be reduced with the other gradients to update the model, right? And then the parameter then server sends the updated model to all the NPUs. But of course, this has your classic challenge with, something being central, it's not going to be scalable. The other approach is more of a completely distributed collective-based approach where compute nodes talk to each other globally to reduce their gradients and update the model to an all reduce operation. So here there is no central entity and you're using some kind of a collective scheme to synchronize and communicate the gradients. And this collective communication is kind of, it comes from classic collective communication from MPI. So exchanging, again, as I said, whether you're exchanging output activations or input gradients really now depends on the parallelization strategy, which I just mentioned, or, and handle either by a collective based patterns or direct point-to-point transfer. So when are collectives needed? Again, it really depends, as I mentioned, on whether you're doing parameter server or collective based. And depending on the parallelization strategy, you may or may not need to exchange things. So this is just kind of elaborating on what I mentioned across different parallelization schemes. So again, just to kind of continue, right, as I mentioned, like my aim here is to just give you a glimpse of some of the challenges in each layer, right? So now we've talked about the workload layer. Let's come to the system layer. So in the system layer, you think about actually designing the compute and memory, your accelerator and communication scheduling. So in the compute end, right, we mentioned that you really want to optimize for some of the key operators that your model is running. So gems are like prevalent across deep learning. And end up consuming, almost 70% of the runtime when training modern deep learning workloads. So essentially, the idea is that during the forward pass, you have a gem or a matrix multiplication of the input feature map and weights. And during the backward pass and gradient computation, you're essentially using the output feature error and multiplying with the weights to get the input feature error and multiplying the delta of the weights and output feature error to get the input feature map. So for accelerating gems, there are like, SIMD-based, vector-based architectures that systems have used. More specialized gem accelerators or systolic architectures are now also almost pervasive, whether it be the NVIDIA tensor cores, the matrix multiplication units in the TPU, and even in CPUs like Intel Sapphire Rapids, there are matrix multiplication engines that are coming out. So the key idea is specialized support for gems and really maximize hardware teraflops. Of course, some key challenges in the compute memory space are that workloads are becoming highly irregular and sparse. So gems are often highly irregular or non-square, especially in the backward pass. And gems are also sparse, right? So this is so sparsity is either explicitly induced during training because you want to reduce the number of computations, so induced in the weights, or of course, if in the input activation, the sparsity just inherently shows up because of things like ReLU and dropouts, right? So this now means that, getting high utilization from your accelerators in the compute end becomes a challenge. So if you have, let's say, a nice regular gem, you have a 4x4, tensor core here, it maps perfectly, you get 100% utilization. But as you start having irregular and sparse gem, your utilization drops. So here, there are, again, in this space, people are looking at different kinds of solutions, right? Either you have one very large matrix engine. This is the example of a Google TPU with a very, very large matrix multiplication unit. Or you can think of the opposite approach of, many, many small tensor cores that are distributed across your accelerator. This would be an example of how NVIDIA's GPUs look like, right, at a high level. So trade-off is, how much data reuse you get within the array versus utilization. And for sparsity, there's a growing interest in adding sparsity support into the accelerators. So NVIDIA's A100 is a classic example where it explicitly supports, 4:2 structured sparsity. And there's, again, growing interest in sparse accelerators. In fact, I guess even at ASPLOS, you'll see a bunch of papers looking at, sparse acceleration support. So some of the trends on the workload end here are, workloads, especially things like transformers, have very low operational intensity. And so which means that they often become highly memory bound instead of compute bound. So memory is a key challenge here. And so there are, again, techniques people are leveraging either like to increase memory bandwidth, right? Let's throw more HBMs at the problem, or let's try out some other solutions to reduce the memory bottleneck. But memory is becoming even more of a challenge. And this is now where things become very interesting, right? So as your accelerators become more and more sophisticated with, let's say, additional sparsity support, better memory, like memory bandwidth, what that means is your training time on the accelerator starts dropping, which is great, right? So your accelerator is faster and faster, but this means that your exposed communication that I mentioned earlier could start becoming a bottleneck. So just as an example here, these are some experiments we ran where, if you, let's say, take a system with 1x of whatever capability for an accelerator today, if you assume that the accelerator becomes 2x or 4x more efficient, it's not like your training time drops. It actually, might remain the same or worse because your communication now starts becoming more of a bottleneck. So this is something that is a worrying thing here, right? So in terms of now communication itself, So I talked about workload parallelization strategy and how this determines the communication. And we talked a little bit about, I mentioned how you have collectives that are running to exchange gradients. There are different kinds of collective algorithms that exist. So reduce, scatter, all gather, all reduce, and all to all are some of the classic patterns that show up with distributed training. So reduce, scatter is used during input-output exchange due to model parallelism. All reduce is used, as I mentioned, both during like data parallel for gradient update or also during model parallelism. All to all is often used for model parallelism, especially when you have the embedding layers distributed in DLRM. But for each of these collective algorithms, there exist many different implementations. So for example, for an all reduce, you could do a ring-based all reduce or a direct all reduce, tree-based, and so on. And I'll briefly describe this, right? So each of these now has implications on how it will utilize your network links. So as an example, this is a ring-based all reduce. So if all of your NPUs are actually physically, this is a logical view of the algorithm, and this maps perfectly if they are actually connected as a ring. So you can imagine, like, on something like the Google TPU, this would be the algorithm used. But if they're connected with some other topology, this might not actually be very efficient. So the algorithm logically says that if I have these n nodes, I'm going to partition my data into n messages, and the algorithm simply says node 1 is going to send message 1 to node 2, 2 will send message 2 to node 3, 3 will send 3 to 4, and 4 will send 4 to 1, and they will locally accumulate this to their local value. And they'll basically keep doing this in turns. And finally, what you have is everybody had a partial copy of the gradient, but at the end of the reduce scatter step now, everybody has accumulated them into their local copy. And then you essentially just broadcast it back to everybody. So now you have the accumulated gradients going back. And so finally, at the end of the all gather step, this is reduce scatter, all reduces reduce scatter plus all gather, you have the full copy of the updated model weights with everybody. So this is a nice algorithm where every step you're using the ring, there is no congestion on the ring at all. But if things are connected directly with all-to-all links, then you don't actually need to split it into multiple phases like this. You can do what's called a direct all reduce, like everybody sends, a copy of like part of the chunks to each other, add them up, and then just, broadcast it back. So in 2 steps, basically you've done with an all gather, right? Or an all with an all reduce. Or similarly for an all-to-all algorithm, if you have an all-to-all connectivity, again, you basically just, send the all-to-all messages to everyone, right? So this is where this notion of topology-aware collectives comes in. So the idea is that depending on the underlying physical topology or building block, you have some topology-aware collective algorithm. So if you're connected physically as a ring, then a ring-based topology-aware collective algorithm makes sense. If physically things are connected in a fully connected manner, then a direct all reduce or a direct all to all that we just showed makes sense. If they're connected via switches, then there's an algorithm called halving doubling that makes sense, right? So these are all implementations that you'll find in collective communication libraries like, let's say, NVIDIA's Nickel, right? Where depending on the way your NPUs or GPUs are connected, it will pick one of these algorithms. These algorithms are also becoming more and more sophisticated as training platforms become more sophisticated, right? So I mentioned earlier about how there's, let's say, people looking at more advanced packaging technologies for creating more sophisticated systems. So imagine that you have some GPUs connected on a package via some high bandwidth links on the package, followed by traditional connectivity across these boards or packages. Then there's much higher bandwidth here than across the links. And so then you have heterogeneous bandwidth, and you have what are known as multi-phase collectives. So we're going to try to do a reduce scatter within the package, then an all reduce across the rows, columns, and then an all gather within the package. Similarly here, right? So these are algorithms that some systems have demonstrated, and again, some of our own work has also leveraged or proposed some of these. And this again shows that as systems become more complex, the algorithms you need to run on them to perform collectives also need to kind of change accordingly. Similarly, then, you need to worry about actual low-level scheduling as well. So once I've decided the algorithm, I've decided an all reduce and it's a ring-based all reduce. Now we get to actual scheduling on the link cycle by cycle. And here again, you have interesting challenges that show up, where if you're kind of, let's say, doing an all reduce on this kind of hierarchical topology, the challenge with all reduce is that as you kind of, as I showed in the algorithm, right, as you're going through these phases, you're reducing things into messages, right? So the message size actually starts reducing as you go across different dimensions. So you start with, let's say, 12 megabyte message. As you're kind of traversing and performing the all reduce, it actually reduces to 3 megabytes everywhere. And then once you to 1 megabyte here, and then as you kind of broadcast it back, it, increases again, right? Which means now you're sending different size messages on these links at different points of time. And so this means that the timing or the time it takes for traversing these messages is also non-uniform. And it can now start leading to, again, pipeline bubbles, right? So you have underutilization on some dimensions of your network because of the way the algorithm was scheduled. And so here you have uneven pipeline stages that can cause network underutilization. So this is actually a challenge that we had identified in some of these modern systems in our ISCA 2022 paper. And we'll briefly actually talk about this when we describe ASTRA-sim as well and how we actually solve this. Just to kind of continue down this loop. So once we've talked about the system layer, now let's get to some of the challenges in the network layer, right, for distributed training. So at the messaging or transport layer, if you're familiar with, different transport protocols, you have things like, TCP, IP, which are, highly flexible because they're completely implemented in software, to the other end where you have like, hardware terminated protocols like GPU direct RDMA. And they kind of have different trade-offs, where they handle, whether like the congestion is being handled at the CPU level or at the NIC level, where the control plane is implemented, data plane is implemented, and so on. But this just shows that there is an interesting trade-off space if you start thinking about network transport protocols here, right? Similarly, if you start thinking about congestion control, right? Like we have a lot of congestion control algorithms that data centers use, but for running distributed training, whether you use window-based or rate-based, whether you use network telemetry or round-trip time, and what are the impacts on training time, what's the best policy when you have different kinds of parallelization strategies. All of these are a lot of open questions in this space. So moving down the stack to endpoint design and connectivity, there's a lot of interesting challenges at the endpoints of your training platforms. So this is another interesting challenge that we had observed, and we published this a couple of years ago. So at a lot of these endpoints, you have your accelerator. Let's say this is a GPU, which is connected to HBM and to the accelerator fabric, right, through scale-up links or scale-out links. And you're running both your deep learning compute tasks, which is the GEMS, and your communication tasks. Right? Your like all reduce involves computations, right, of adding the gradients up. So all of this is running on, let's say, the GPU. And so what happens is you have sharing of your code. So even though you have some amount of compute flops available for GEMS, not all of it is actually available because your communication tasks are using some of those. You also have memory bandwidth contention, right? So the memory bandwidth is now being shared by compute tasks and communication tasks, which ends up slowing things down. And in fact, this is something that we measured when we did a communication replay for a DLRM workload, where we saw that you actually end up having slowdowns. So if you were to just run communication as opposed to trying to overlap computed communication, you actually end up having slowdowns because of memory contention and compute contention issues. So we then possible solutions here in this work, this was an ISCA paper we had, where we created a special small accelerator that was optimized for like training communications that essentially freed up the compute resources and memory bandwidth purely for compute. So it kind of has communication not affecting compute, so you kind of have efficiency going up. There's also alternate approaches. There's, NVIDIA had an interesting paper where they observed a similar challenge and tried to offload some of these communication tasks onto the switches itself so that your GPUs are, available for compute. So there's a lot of interesting challenges and opportunities when it comes to endpoint design. So moving down the stack, so we've talked about the endpoint. Now, how do you connect them up physically, right? What kind of topologies do you use? And this is again where there is no clear right answer, right? Like you'll see all the way from, the Google approach of, let's say, a torus topology that's used, to NVIDIA's approach where they're kind of switch-based hierarchies that they've built, to Cerebrus's approach where like thousands of accelerators will be connected densely using a mesh on a package, right? What is the right approach? Again, the jury is out on that, right? So all of these are interesting research questions here. And once you start looking at topologies, again, what kind of, how do you actually design these topologies? How do you kind of decide whether it's a completely homogeneous, system, or do you do, some more dimensions in one side or the other? All of these are interesting open questions. And again, the challenge becomes, because I mentioned like how you have these collective algorithms all reduced running where the message sizes are changing, right? So some of these have implications on how your topology is actually set up. And if you have an asymmetric topology, these are some experiments we had done in our original ASTRA-sim paper, where it was showing how changing the collective algorithm or the number of phases can actually have a huge impact on communication time as well. And finally, like to the lowest level of the network stack, like so the network implementation, there's several different kinds of systems that one can build. And we did some experiments where we tried to identify like the size effect of different size switch buffers and how it affects overall performance. So again, these are some experiments that I won't go into detail that our paper has, but just trying to show that, once you come into low level switch design, buffer sizing, arbitration, there's again a lot of interesting open challenges here when it comes to designing specialized systems for ML training. So essentially, the question now is, well, how do you navigate this codependent design space, right? For each level, I tried to introduce some challenges, but as I mentioned, ultimately the challenges kind of get cross-coupled because you're trying to, co-optimize this entire system across all of these layers, right? And that's where ASTRA-sim comes in. So our goal with ASTRA-sim was to, like faithfully replicate these behaviors inside the simulator. So we have what's called a workload layer, which captures the training loop, and we'll go into that when we describe the simulator. We have the system layer that captures the communication mechanisms and all of the scheduling the issues that I talked about. And we have a network layer, and that's the beauty of ASTRA-sim, where you basically plug in different kinds of network models or simulators depending on the fidelity you want and depending on the kinds of things you can study. So we'll talk about how you can plug in an analytical model, Garnet or NS3. And so essentially the workload layer supports different kinds of parallelization strategies and training loops. And we also have a graph-based execution engine that we've recently added. The system layer essentially implements several different kinds of collective algorithms. So I described several collective implementations. So we already implement like ring-based, read-based, algorithms. We implement several scheduling policies as well. And compute times are fed in externally via some other simulator. And on the network end, you essentially can model different kinds of topologies, flow controls, link bandwidths, and so on. And you have different plug and play options for analytical network backends, Garnet and NS3. And finally, what does ASTRA-sim report? It reports end-to-end training time, communication time for each op, amount of exposed communication, total compute time, exposed communication time, and several like network backend specific reports, right? So depending on the network backend you use, you can actually see all of these reports and optimize. So to kind of summarize like my part, essentially, large model distributed training is an open, ongoing open research area. Many emerging AI supercomputers are being built specifically for this problem from several different companies, and co-design of the algorithm and system offers actually high opportunities for speed up and efficiency.